Welcome back. Let's talk about functions. We'll start off with some definitions and then we'll work our way over to encryption and hashing and then round up with some syntactic considerations that are related to writing code. Let's skip to the end here and then we'll come back and go through this in detail, but at the end of this section we're going to have this little flow chart right here. Basically, we're going to start off with relations, and there's a couple of properties of relations that determine whether something is a function or not. And then if it is a function, there's a couple more properties that determine whether it's reversible or not. And that's kind of where we're going with this, okay? That's the answer jumping ahead. And we'll look at that again at the end. But starting off simple and building up to the end, we have this idea of a function, which can be thought of as a process with input and output. Typically we use a symbol x to indicate the input and then f of x to indicate an output, and then the process itself can be called f. We can look at what we know already from analytical geometry. Here's a classic function, the x squared function. The inputs are on the x-axis and the outputs are on the y-axis. So for example, if x were 2, then you'd get an output 4. Likewise, if x were minus 2, you'd also get a 4. And if the input were 4, you'd get a 16, like that. So the input is defined for real numbers, negative and positive, and the output is positive only. There's this little function. Here's another one, the square root function. So here we have to limit the input because we don't want to take the square root of a negative number. That would result in a complex number, which is something we don't want to talk about right now. So here the input is the positive set of real numbers, and the output is also the positive set of real numbers. So you could write this using set theory notation. You could express the function f as the set of all ordered pairs x comma f of x such that there's some condition of what defines a legal input of x, like x squared or square root of x, something like that. So this needs this what defines legal inputs of x needs a little bit more clarification depending on the situation, the example. So the point here is that functions from analytical geometry can be thought of as relations, and they are relations. A function is a special kind of relation. The other thing we can say before we move on is here we're using the set of real numbers which have certain characteristics, right? In math, regular math, the real numbers are considered to be infinite. They go off to infinity because in our number system we can keep adding digits to infinity. And the other thing about them is that they're defined for every point on the line. Okay, that's the real world, or is it? It's the math world. But in the computer world, which if you're a computer scientist, the computer world is actually the real world. So it's a little bit philosophical there, but anyway, in the computer world or the discrete world, we don't go to infinity because our machine is a finite box. It only has so much space in it. And the second thing is we can't define points at any point. So we call that the discrete world versus the continuous world. So we're going to be dealing with discrete sets, or numbers that are defined for a particular range and that also defined for a particular precision. So we saw that in our floating point homework where we looked at floating points. They have a particular range and then they have a particular values that they're defined on. They have a particular precision. All right? And we can restrict our sets a little bit further just to make things simpler to things like natural numbers. Okay, so we're just going to deal most of the time with natural numbers and integers and smaller sets than that. But keep in mind that this same kind of thing could apply to discretely defined floating point numbers. All right, so here's a little easier to deal with set for us, the natural numbers, or sometimes called the counting numbers, starting at 0 and going out to infinity. So this is still a mathy thing. That is, to put it in an actual machine, you would need a finite set, but here we're going to use the infinite set. So we have the same squaring function, but on integers. And so f is the function consisting of the ordered pairs n squared, such that n is an element of the natural numbers. So this is the set notation, or the actual ordered pair notation for this function. You take all of the elements of the original set and square them. So square 0, square 1, square 2, square 3. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, like that, all the way out to infinity. It would look like this if you plotted it. So this is a discrete function. That is, it's not defined continuously at every possible intermediate point. It's only defined at discrete points. That's the nature of computer numbers, discrete numbers. And this particular one goes to infinity, but really in a computer you would limit the range out to some maximum value. For example, like if you had a 32-bit register size in a computer, then 2 to the 32 is approximately 4 billion. Nowadays, PCs have 64-bit, so the maximum integer that you could store would be 2 to the 64, which is a pretty big number, but still it's finite. All right, it's time for the formal definition of a function now. So a function from set A to B, we have this notation, f colon a arrow b. Well, you say that f is a function that maps the set A into the set B. So f is a relation with an additional two properties, and those properties are robust and deterministic. So briefly stated, robust just says that the function can handle all of the inputs. That is, it produces an output for every possible input. It won't break when you give it an input. It knows what to do with every input. And then deterministic means that it always does the same thing with that input. That is, each input will give you the same output every time. All right? So here's a guy that's neither robust nor deterministic, this little guy. So here we've reduced the input set to truly a discrete set. It's finite and it's only defined at these 5 values. You know, that's really something that would be in a computer, you know, finite and discretely defined. And I've just chosen some ordered pairs out of this Cartesian product just to review a little bit. So the cardinality of this set is 5. So this set crossed onto itself, that is the Cartesian product of this set would have a cardinality of 5 times 5, or 25. So there's 25 possible ordered pairs that you could generate from this set. And then just pulling out, for example, we're pulling out 5 ordered pairs just to generate this little guy expressed as a digraph. So this guy's not robust because this 5, it'll break. There's no arrow leaving 5. That means when let's say you wrote a function in a program, what that means is when you call that function with the value 5, it crashes. It's not robust. It doesn't know what to do with 5. Okay, so that 5 without an arrow leaving fails the robustness check. The deterministic check fails on this 4 right here because this 4 has 2 arrows leaving. It shows up here 4 and 4. So that fails determinism because it basically means that if you call this function and give it a 4, sometimes you'll get a 3, sometimes you'll get a 5. You don't know what you're going to get. It's like flipping a coin. So this is neither robust nor is it deterministic. So it's not a function. It's still a relation, but it's not a function. All right. Let's look at one that's both deterministic and robust. This guy right here. So this guy is both deterministic and robust. It is a function because it has both of these properties. So let's back up here. So here's the original set. Here's some pairs that we've pulled out that looks like this on the digraph. The original set, 1, 2, 3, 4, 5, is here. It has an arrow leaving every one of these guys. So this guy knows what to do for every possible element of the input set. It's not going to break. That is, it's robust. There's also only one arrow leaving each one of these guys. So if you input a 5, you'll always get a 4, nothing else. If you input a 3, you'll always get a 3 and nothing else. So it's deterministic, it's robust. Okay, so this relation has these two properties. Therefore, this relation is also a function. Let's review this in terms of analytical geometry. The real numbers that we looked at earlier, here's the same function we saw before. This guy's robust and deterministic. If you define the input set as the real numbers, so that means f of x is a relation on the set of real numbers. That means the input set is all the real numbers. The input set is positive and negative real numbers. So the entire set of real numbers is covered. That is, it knows what to do for every possible real number value. You could give it any number on here and it'll produce an output. These arrows go up forever, right? So, you know, out forever on the x-axis will give you an output. So it's robust. It's also deterministic in that every input will give you the same output every time. Like if I do a 2 for the input, I'll get a 4. If I do it again, I'll also get a 4. Okay, don't confuse that with the fact that this one also gives you 4. So this one here means if I enter a -2, I will always get a 4. So for -2 will always give me a 4. 2 will also always give me a 4. It's the output side that you're interested in. You're looking for the lack of duplicates on the output side. Duplicates on the input side are okay. Okay. So this is a function. This guy here is not a function. This, you may have seen in your analytic geometry classes that there's something called the vertical line test. That if a function or a curve, rather, if a curve crosses the vertical line more than once, then it's not a function. That's because it's not deterministic. Right here, if this were 2, I was talking about 2 before a second ago. If this were 2, sometimes I'd get this value, sometimes I'd get that value, sometimes I'd get that value. There's 3 possible values, so it's not deterministic. Therefore, it's not a function. Is it robust? Well, it depends on how you define the input set. Here I'm defining the input set as real numbers greater than 0. So if I define the input set this way, greater than 0, then it's robust because it knows what to do with every positive, with every element of the input set, which are positive real numbers. So it's robust, but it's not deterministic. Therefore, it's not a function. Right there. Okay, here's one with the opposite situation here. This guy here is not robust because it's not defined at this point right here. There's a little hole. So if you give it this input value, it'll break, crash, you know. But it is deterministic. That is, it passes the straight line test. There's only one point on any, if you drew a vertical line, there's only one point on that line where it crosses. That's the robust part, but that's the deterministic part. But here it's failing the robustness part at this point. It doesn't give an output on that point. So this guy is not a function. Okay, so before we go any further, we need to make a few definitions. We need to define a few things. So we have a couple of definitions: the domain and the range, and then the codomain. So the domain is all of the input set, and the range is the exact outputs, the exact output sets, technically. But often that's inconvenient, and often we'll use the codomain instead of the range. So the codomain is any set that's big enough to contain the range, so big enough to contain the possible outputs. So typically we'll use B in the codomain. Well, it's best to look at an example here. So here's our squaring function from before, defined on the natural numbers. So the input set is the infinite set, n, the natural numbers going from 0 out to infinity. And we say f is a function that maps n back to n. But we're using the codomain here for convenience. It doesn't actually map into n exactly, right? Because look at a little further. So f is the squaring function. It just takes the input and squares it. So this is what it is here. It's 0, 0, then 1 squared is 1, and 2 squared is 4, and 3 squared is 9. So the range is the exact possible output. So the range is 0, 1, 4, 9, 16. That's the range exactly. But it's inconvenient to talk about that. In fact, if we did that, we wouldn't be able to list n on the output side here. We'd have to list these numbers exactly, which is inconvenient. So what we'll do is we'll consider the n to be the codomain. Okay, because n is big enough to contain this, right? And it's similar to the range. And people, know what you're talking about when you say f maps n back into n. There's an integer in and there's an integer out. That's good enough, but we're talking about the codomain here. Okay, so for convenience, we'll use the codomain, but really, the range can be less than the codomain. The range can be a subset of the codomain. Okay, so that becomes important later on as we talk about some more properties. So there's that definition. Okay, another thing we got to talk about is this idea of composition of two functions. This is the same as what we saw in relations. It's the same thing, really. But here it is again. So if we have two functions, f and then g, and if we apply f to x first, we get f of x. And then we do that again. We take the output of f and apply g to it. We get, you could say, g of f of x. You could say that. Or you could say g composition f. Or you could say g dot f. So here's a little example. I got two functions, f and g. So f is these ordered pairs right here, and g is these ordered pairs. So f in the diagram, 1, 1, 1, 1, 2, 2, 3, 3, 3. That's f. And then here's g. G is 1, 3, 2, 1, 3, 3. So we're taking these input values and putting them into f, and we get these output values. And then we're taking these output values and putting them into g, and we get these guys. So the whole thing together is g composition f. And g composition f gives you this other set of ordered pairs. So to generate these, you'll just start at the 1 and follow the arrow all the way to the end. So 1, 3, 2, 3, 3, 3. So these are all functions. F is a function, G is a function. The composition is also a function, but let's check it. So F is a function if it's robust and deterministic. Is it? Yes. There's 1, 2, and 3. All three elements. Well, you need to define what the input set is here, really. If you define this input set as 1, 2, and 3, and say that f maps a back into the codomain a, not the range, but the codomain a, and g likewise maps a back into a. I should put that on here somewhere. But then now we can check for robust, because we need to know the original set A to check for robust. So if the original set is 1, 2, 3, then this guy's robust because there's an arrow leaving these guys. So F is robust because there's one arrow leaving every one of these guys. And there's exactly one arrow leaving every one of these guys. Therefore, it's deterministic. So F is robust and deterministic. F is a function. What about G? G is robust because there's one arrow leaving every one of these guys. And it's deterministic because there's exactly one arrow leaving each one of these guys. So G is a function. What about the composition GF? Is it a function? And it is because it's robust. The input shows up, or every element of the input shows up as some element of some ordered pair. There's a 1 there, there's a 2 there, there's a 3 there. So it knows what to do with 1, 2, and 3. It's robust. And there's only one showing up in here as the first element. And there's only 1, 2 showing up. And there's only 1, 3. Or in the digraph, there's an arrow leaving every element of the input set. That's robust. And then there's only one arrow leaving every element of the input set. That's deterministic. And that's all we care about. Over here, the fact that 2 is missing doesn't matter. We don't care about the output side for robust and deterministic, just the input side. All right. So F and G are both functions, and the composition GF is also a function because all of those guys are robust and deterministic. So that's for this particular example. It's possible for there to be other variations on that. I'll leave that for you to think about if you want. But anyway, here we're just kind of presenting the idea of composition. Okay, let's kind of move on to the next stuff. Or before we leave that, we could be thorough and look at some other permutations of G and F. Like here we did F first and then G. That's G dot F. That's this first guy that we already did. You could flip it around and do G first and then F, and you'd get this. I'll leave that up to you to do. And you could apply F to itself twice, and you'd get these. Or you could apply G to itself twice. And you can do that if you feel like messing around with that. But let's kind of move on a little bit here. So we have this formal definition. So if F is a function that maps the set A into set B, and G is a function that maps B into C, then the composition G dot F is a function that maps A into C. So it's like transitivity. You can say that G of F is a function that maps A into C, and you sort of skip over B. It's transitivity. Then there's this, which is kind of a bear to even think about, but let's go through this at least once. So we can define the composition G of F of X, given by this notation G dot F, is the set of ordered pairs AC, where these three conditions are true. Where there exists a middle element, little b, in the middle set, and there exists an ordered pair AB in F, and there exists the ordered pair BC in G. We could go back to this guy way up here and check that and see if this applies to this dude right here. Let's take let's just analyze this guy and see if this guy here, and see if it matches this definition here. Kind of tedious, but so let's take 1, 3. That would be an AC. So we got to look for all three of these. Is there a AB in the first F? Is there a 1? And in this case, it's going to be a 1. This is it here. So the little b is 1. Little b is an element of this guy, so that matches this thing here. And 1, 1 is in F, and 1, 3 is the BC part, is in G. 1, 3. So it's you know, it's not that fun. But I guess I'm presenting this. The reason this is here is that if you were to, this has enough level of detail that if you were going to code it, you know, you could. this is it's too coded. Don't worry, I'm not going to ask you to do that. But, to write code, you need to get it, simple enough for a computer to understand, right? Dumb enough for a computer to understand, as we say, because computers are actually pretty dumb. All right, they just do what you tell them, right? Okay. So let's say we've established that a relation is a function. That is, we've established that it's robust and deterministic, therefore it's a function. Okay, so now we're talking about functions, and we can analyze functions a little bit further, right? So a function may have two properties. It can be one-to-one, and it can be onto. These are the inverse, or these are the opposite of robust and deterministic, basically, right? So here where what you've defined as the domain and the range start to become more important, to keep this straight in your head. And the best way to understand this is with an example. So I got a couple of guys that are right here. So let's see, we got this little example that is a function on the natural numbers from 0 out to infinity. We're going to look at some other examples that deal with the real numbers and the integers, but this first example is on the natural numbers. Well, actually, this first example doesn't even matter what the input set is on. It fails injectiveness because there's 2 shows up twice. That would be true whether this was a function on the real numbers or on the integers or on the natural numbers. It doesn't even matter what the input set is here. The 2 shows up twice, so it fails injective. 1-to-1 is injective. So you just look at the second element and see if it shows up twice, and that's enough to fail injective. Okay, the second one, we have to define the input set here. And we're using the natural numbers. We're saying F2 maps the natural numbers back into the natural numbers. And here we're using this is the codomain, right? Because we're talking about the squaring function. Remember, the squaring function the output set doesn't contain every element of the natural numbers. It contains a subset. So for convenience, we're using the codomain here. Okay, there's that. But if you restrict the set to dealing with just the positive integers or the natural numbers, then it's injective. Because, like here, 2 squared is 4. And so the 4 only shows up once if you just have the positive numbers for the input. If you use the integers for this guy, then it would fail injectiveness because you would have 2 and minus 2. In fact, I think I got that down in here. Yeah. Okay, so how you define the domain and the range and the codomain kind of matters. So like here, if you did real numbers, then it's not injective because the second element, the 1.21 shows up twice. 1.1 and positive 1.1 and negative 1.1 both give you 1.21. So this fails injective. It's kind of failing the horizontal line test. It fails for real numbers. It fails for integers, which are positive and negative. Okay, so it fails in the continuous world. It's not injective in the continuous world, and it's not injective in the discrete world. If you use real numbers in the continuous world, you use integers in the discrete world, it fails injectiveness. But if you use just the positive numbers, then it's injective in the discrete world. Fun, all right? So we can look at some onto examples here. This guy is onto because it covers the entire codomain. Well, I'm saying codomain. Now here you got to be really careful. let's say this, the range, which is what range is, the exact elements. The range consists of the entire output set for this example. So here, look, this is the set. So this guy, set A. So F maps A back into A. Okay, so it maps 1, 2, 3, 4 back into 1, 2, 3, 4. So it's onto, because every element of the, in this case, this is the range exactly. Every element of the range is covered. So it's onto. Now here, when we list this notation right here for the squaring function, we're actually talking about we're actually using the codomain here for convenience, because the actual range is 0, 1, 4, 9, 16. That's the range. So it depends whether this is onto or not, depends on what you're using here on the output side, whether you're talking about the codomain or the range. If we use the codomain, that is the natural numbers, then it's not onto, because it's missing all these other values in here, right? It's missing 2, 3, 5, 6, 7, 9, all those. None of these values show up as the second element, so it's not onto. It doesn't cover the actual set of natural numbers on the output side. It's not onto the natural numbers. Okay. So you need to be careful. So once again, it's not onto if you actually are talking about mapping back onto all of the natural numbers, then it's not onto. So you need to be careful. But if you said that this thing maps onto just these guys here, well, then that's different. I'm going to stop talking right there. Okay. A couple other things. We've got the inverse of a function. Okay, look, there's a little bit of confusion here, a little bit more confusion talking about the inverse of a function. So a function is a special kind of relation. Now you can always take the inverse of a relation. You just get another relation. But what we're talking about here is when you take the inverse of a function, is that inverse a relation or is it another function? That's what we're trying to get at here. So given a function, we check if it's onto and one-to-one. And if it's both of those things, we call that bijective. And if that's the case, then the inverse of that function will also be a function. Otherwise, the inverse of that function is just a relation. Now, to make things a little bit confusing in math, sometimes they say the inverse exists. What they really mean by that is that the inverse is a function. Because technically, you can always take the inverse of a relation. It's just that that inverse of a relation might not be a function. Okay, so once again, when we say the term inverse exists, what we typically mean is that the inverse is actually a function. Here's an example, a couple of examples actually. Let's see what's going on here. So I've got this input set 1, 2, 3, 4, and I have a relation R that maps A back into A, given by these ordered pairs, which looks like this. So first we check, is R a function? And so we're going to check, is it robust and deterministic? So R is robust because there's an arrow leaving every one of the original input set. That makes it robust. And then there's only one arrow leaving every element of the input set. That makes it deterministic. So R is a function. Okay, now that it's a function, we can check, is it one-to-one and is it onto? So we need to carefully define the output set. In this case, the output set is carefully defined as these exact values. So, no confusion like there was with natural numbers. But then all you got to do is check, is that output set totally covered? And it is. There's an arrow leading into each one of these guys. So that's onto. And then the one-to-one check is there exactly one arrow going into each one of these guys? And there is. So this is one-to-one and it's onto. Therefore, its inverse will also be a function. And this is the inverse right here. The inverse is just flipping the pairs around, right? So 1, 1 becomes 1, 1. 2, 4 becomes 4, 2. 3, 2 becomes 2, 3. 4, 3 becomes 3, 4, right? We just flipped all the pairs around. It looks like this. This is a function, right? Because it's robust and it's deterministic. One and only one arrow leaving this side. Okay, so the inverse of this is this. This one happened to be a function. That function happened to be robust and deterministic. Therefore, its inverse is also a function. So, I hope I said onto and one-to-one and onto. That's what I meant to say on this side. But one-to-one and onto is kind of the opposite of robust and deterministic. All right. So if the inverse exists, and by that we typically mean that the inverse is also a function, we say that R is reversible. So if you applied this twice, you'd get back to the original input. In other words, you go from 1 to 1, then put that 1 back in, you're back to 1. Or let's do a little harder, a little less obvious one. 2 in, you apply a R, you get 4 out, and then you put the 4 back into R1, like you're going to get 2. So you start off with 2 and you end up with 2. So the composition of this gives you back to the original. So the composition of, applying a function with its inverse function just gives you the original stuff. It looks like you didn't do anything. It looks like you started at 1 and went back to 1 and 2 and 2 and 3 and 3 and 4 and 4. It looks like you didn't do anything. So don't do this when your boss is looking, because you actually applied the function twice and you got back to where you were. It looks like you did nothing. So you got to be careful when you're writing programs that you don't write a program that does the opposite and it looks like you did nothing, you don't get paid. So here's an example of where the inverse is not a function. So we have to go slow and we have to define what we're talking about with the range and the domain and all that stuff. So we're dealing with the set of integers. So this is positive and negative values, and then we're saying that R maps integers back into integers. So here I think we're using the codomain because we're talking about the squaring function. It's not going to map every integer. So it's R is first we have to check if it's, well, back up for a minute. We already established that R is a function because it's robust and deterministic. We figured that out, and go look back at that. So now that we know that this is a function, we're going to do the one-to-one and onto checks. So the one-to-one check, you look at the second element, you see that 4 shows up twice, for example. That's enough to break one-to-one. And then it's not onto because it doesn't map back into the negatives. There's no, it doesn't map into -4. It doesn't map into any negative values, actually. It only maps up into the positive values. So it fails one-to-one and it fails onto, so the inverse is not a function. The inverse is just another relation, but not a function. All right, what do we got? So a little bit of, well, actually, 2 more examples. This guy's reversible. So here we have a set A, bat, cat, and an output set 0, 1. And so f is a function that maps A back into B given by these ordered pairs here. So you put in a bat, you get 1. You put in a cat, you get 0. So you could draw the digraph, bat, cat, and 0, 1. So you put in a bat, you get a cat, or 1, and you put in a cat, you get 0. So it's robust because it handles bats and it handles cats. And it's deterministic because bat will always give you the same output and cat will always give you the same output. So it's a function. because it's robust and deterministic. And then this is f, and then f minus 1 is you flip these order pairs. So 0 would give you cat and 1 would give you bat. So this is the inverse. The inverse is also robust and deterministic. So this is also a function. But I sort of skipped a step. You could just look at this and first establish that it's a function. Then you could look to see whether it's one to one and onto. So you look at the output side, and the output side is 1 to 1 and onto. Therefore, the inverse should be also a function, and it is. And if you do the composition of these guys, you're just gonna get bat bat and cat and cat cat. So this guy's reversible. Let's look at one more that is not reversible. Be this dude. This guy here is not reversible. So I've got a set of area codes A, 215, 209, 303, 707, all these different area codes. And then I've got these little numbers here, just 0 through 4. And then we say f is a function that maps the set A into the set B, given by f is a set of order pairs f of x, such that f of x is the sum of all the digits mod 5. So let's do that. So sum all these digits, 5, 6, 7, 8. The sum is 8, and then mod by 5. 5 goes in once with the remainder of 3. So there's one pair. And this guy here, the sum of the digits is 11. Mod by 5, 5 goes in twice. That's 10 with the remainder of 1. This guy here, the sum is 6. Mod 5, you get a remainder of 1. So these two elements here, this 209.1 and this 303.1, they map to the same element here. So it's not 1 to 1. This guy, this function maps here. It's not 1 to 1. So f is not reversible. In other words, if you put in a 209, you get a 1, and then if you put in a 1, there's no way to get back to 209 reliably. You put in a 1, you might get 209, you might get 303. So this is not reversible, it's a hash. Okay. So that's it, So it's easy to get kind of confused on what the process is. So here's basically the thing in the flow chart, which we started out with at the very beginning. So let's see. Sometimes you want reversibility and sometimes you don't. It's kind of what it comes down to. So you start off with a relation R, which, set of ordered pairs. You do this check. You check is it robust and if it's deterministic. If it's both of those things, then it's a function. And if it's not, if it fails one of these tests, then it's just a relation. It's not a function, but it's just a relation. Okay. And once you know that something's a function, you apply 2 more tests. You check, is it 1 to 1 and is it onto? That is, you look at the output side. Over here, you're looking at the input side and performing some checks. Here, you look at the output side and determine some checks. And if it passes both of these checks, then the inverse of that relation will also be a function. Otherwise, the inverse is just a relation. Here's where we say the inverse doesn't exist, but what that really means is that the inverse is not a function. So be careful with that when you see that in the math book. Anyway, the bottom line is, for us, is that if it's reversible, you can use it for encryption, right? You can go from bat back to bat. But if it's not reversible, you can use it for a hash. That is, you can go from 209 area code to 1, but you can't get back. Okay, so reversibility is typically used in encryption because you need to get back. And then hashing is typically used when you don't want to get back for some reason. The classic computer science example of hashing is, well, one of the examples is password security. Like, you know your password, and in some systems you're the only one that knows the password because they don't store your password on the other end. When you type in your password, the system will do a hash of your password and send just the hash. That way your password is not stored anywhere, just the hash is stored. Now it's a little bit more complicated than that, but that's the part of the basic idea is you don't want to be able to go back. I use that on the website to post your grades, right? So that only me and you know your student ID, because I'll post it by a hash because I'm trying to protect your privacy a little bit. Okay, that's the basic idea. And Bitcoin and other things is another example of uses hash. That's a lot in the news nowadays. Okay, last thing we'll wrap this thing up with is some syntactic considerations. We've been talking about functions from a kind of mathematical view and their point of view. Okay, so I want to expand that and think about the syntax when you're writing code. So there's expressions and there's functions. So an expression is something like this. This is a unary operator, negation, right? If I just have a number like 2 and I want to get a -2 out of it, I'd say -x, and it would, reverse it. But this is what it looks like in an expression, where the operator is the minus sign and the x is the operand. Okay, that's an expression, but you might express that same thing in code with a function. So this is a unary operator, which is similar to what we've been talking about. It'd be something like 2, -2 and -2, 2. Okay, so this is kind of to fit what we've been talking about. But there's also binary operators. So here you have 2 operands, A and B, and you have the operator plus. But you can also express that as a function. So, here, this might look like something like if you did 2 + 2 is 4, this would be, in function notation, it'd be, the ordered pairs would be, well, it maps an ordered pair back into a single value. So it'd be something like this. Would be one of the elements, and then 3 plus 3 is 6. So it gets a little more complicated. From most of this lecture was talking about single elements back into single elements. Here we're talking about pairs back into single elements. But the point is, studying functions and their properties can kind of help you understand what's happening in your code. And more than that, a lot of times we write expressions. Like when we write arithmetic, we're writing expressions. But what we're really doing is we're doing a kind of function, mathematically speaking. That is, you can understand what's happening when you write expressions if you think of them in terms of function theory. All right? So, that's what this material is really about, is to help you think clearer about what's happening in your code from a kind of mathematical perspective. So, when you write the code, you type in the stuff. Hopefully it's a little less buggy. All right. That's it. Hope that was useful to you. I'll see you next time. Bye.